Very good morning to everyone. I would like to thank for the organizer of this webinar, and I'm happy to share my research topic, solar-driven chemical and fuel synthesis for sustainable future. So before start my research work, I would like to show you my transition. After my master, I joined with Dr. C. Karnaran sir in VH Anderson College, Virudhunagar, and I did PhD there from 2010 to 2014. And then I have been awarded Swiss Government Excellence Scholarship for my postdoctoral studies in Switzerland. There I spent more than 4 years as a postdoc, and then after my contract ends, I joined in University College London. So here is the layout. We are going to see two solar driven methods. One is to synthesis ammonia, the second one is to produce hydrogen, and then what are the future outlook, and then question and answers. So let us start with development of green method for ammonia production. So let's start with the interesting story or the brief outlook of why this project or what is the scope of this project. Basically, nitrogen is an essential component of the building blocks. If you look at the DNA, RNA, and proteins, there you can see the nitrogen as an important element. Okay, from where we can get this nitrogen? If you look at the atmosphere, it has 78% nitrogen. But the question is, do we really inhale the nitrogen similar to oxygen? The answer is no. The reason is that the triple bond is very difficult to break, and we cannot easily break as easy as oxygen. Then how, or who else helping out? How do we take the vital nitrogen? Interestingly, nature does that. If you look at the bacterium called rhizobium, which are mainly lives in leguminous plants types, and that can convert the atmospheric nitrogen into the nitrogen compounds, which is a fertilizer we say. And here is the brief equation how the natural nitrogen fixation happens, and the 16 molecules of ATP provide the energy required for breaking this nitrogen triple bond in with the help of the electron and proton. Mainly proton can be obtained from the water. You might ask, is that is the only source, or is there any other source can also fix the nitrogen? Yes, of course. Lightning, organic manure, and biological soil crust can also fix the nitrogen fixation, um, and by eating these crops like the rice or wheat, whatever we obtain from the plants, and the vegetables and fruits from the trees, through that we can take the nitrogen into our body. Now the question is, are all of these natural sources enough to feed the world? Let us see from these statistics. If you look at the world population currently exceeded 7 billion, and here if you look at the world population fed by synthetic fertilizer, it's about 50%. So currently 50% of the world population alive today because of the ammonia based fertilizers. So how this ammonia based fertilizer has been synthesized, and what who invented this important chemical process? So here they are. Fritz Haber and Karl Bosch, these two German chemists, made industrial nitrogen fixation. One molecule of nitrogen combined with three molecules of hydrogen producing ammonia in the presence of iron, some alloy catalyst, and under high temperature, high atmospheric pressure condition. And for this significant invention, both of them were awarded Nobel Prize. So now the question is, do we still need to follow or use this industrial Haber-Bosch process, and why we really uh, proposing this solar driven ammonia method? We are going to see what are the darker side of the Haber-Bosch process. So mainly this pollutes the environment heavily, and also we have to supply a lot of energy to carry out this industrial nitrogen fixation reaction. It consumes a 5% of world natural gas. You may wonder, the natural gas is methane, nothing but methane. And as we have seen in the previous slide, we have to have hydrogen to combine with nitrogen. So the source for hydrogen currently is obtained from methane. And you see, at the end of the hydrogen extraction, it releases so much of carbon dioxide, and this globally accounts for 1.6% emission, that leading to global warming, climatic change. We know carbon dioxide is a greenhouse gas which impact the environment significantly. So the energy spent for this single chemical reaction consumes approximately 2%. And with this 2% energy, one can provide electricity for the world 1 year. So that much energy has been used for this single chemical reaction. So these are the experimental condition: 400 to 600 degrees Celsius in the presence of catalyst, and for 150 to 200 atmospheric pressure. So that's why we are focusing on two sides. One side, we don't want to pollute the environment. On the other side, we want to uh, save the energy, or we want to use less energy. So energy plus environment issues. So these are the two objectives in front of the chemist who really want to make alternative to this Haber-Bosch process. So there has been research effort over the last 30, 40 years, and still we were not able to come out with suitable technology for practical application. And the reasons are mainly because we have we need 410 kilojoule per mole to break the first bond in the triple bond molecule of nitrogen. And if you look at the gap between HOMO and LUMO, this is very high. And as a chemist, we obviously know when this HOMO LUMO gap is higher, this is highly stable. And also it has very low proton affinity, so it cannot easily get hydrogenated. However, we were able to show or prove the alternative routes to synthesize ammonia. So the first one is electrochemical way. In this case, we apply the external bias, some voltages, to bring nitrogen and hydrogen to form ammonia. But if you look at the source for producing the voltage, again we have to spend a lot of energy, and this kind of electrochemical way not feasible in gas phase. So this is too far for a practical application. And some inorganic chemistry researchers, they are trying to synthesize inorganic complexes which looks similar like the enzyme present in the bacterium called nitrogenase. And this, although able to show it can produce ammonia, it mainly failed because of its poor stability. And the synthesis of this inorganic complexes is really challenging and very difficult one. That's why people currently more focus on this solar driven nitrogen fixation, and we hope that uh, compared to the previous this electrochemical and inorganic complexes method, this solar driven method can be a potential alternative in the coming years. And here you can see these are the advantages we get out of this solar driven process. Like this is highly sustainable. As we know, the solar energy is highly sustainable, and the materials we use like metal oxide or polymeric semiconductors, they are earth abundant, and this is very important. Water can be used as proton source. In the traditional Haber-Bosch process, we are using methane as hydrogen source, here water. So at the end of the process, we don't pollute the environment. So there is no carbon dioxide emission at the end of the process. That's why all the developed countries, even all the developing countries, they are focusing on zero carbon economy. So this is the simple schematic explaining photocatalytic or solar driven nitrogen fixation, and it involves mainly three steps. Charge carrier generation. So these semiconducting materials, when we shine a light on it, the light supposed to have energy higher than the band gap, it can able to excite the valence band electron to the conduction band. And this is the first step. So we have to have the suitable material which generates more number of charge carrier inside. And the second step, once charge carriers are generated, it's supposed to move to the surface of the material in order to see or in order to enter into the absorbate. So that's the second step. For that, imagine there is a nano material, let's say 100 nanometer size, and there is a 1 micrometer, which is 1000 nanometer size material. Uh, in this case, the diffusion of the carrier to the surface is much faster or easier in 100 nanometer size material. So it is important to use the nanomaterial to make it this diffusion of the carriers to the surface. And the third process is, once it reaches the surface, the molecule, here in our case it's nitrogen, it's supposed to absorb very well on the surface of the material. Otherwise, if it is a poor physical absorption or some van der Waals kind of absorption, there might be a poor charge injection from the material to the nitrogen molecule. So these are the three important steps people are working to optimize the efficiency of the process. Okay, in my case, I worked in EPFL, Switzerland. I developed the plasmonic green method for ammonia synthesis. You probably ask, what is this plasmonic method? Plasmonic method is nothing but the metal which are active, their conduction band electrons are active in the visible light. Let's say gold and silver. These two are very common plasmonic nanomaterials. When we shine a light on these metals, the conduction band electrons oscillating resonance to the wavelength of the incident light, and after some time, this resonance oscillation release the energy. Once the resonance is stopped, it release the energy, and that energy excite the electron above the Fermi level, and this electron can be used as a plasmonic hot electron for breaking the any absorbate molecule. At the same time, this kind of oscillation also generate the electric field on the surface of the metal, and this electric field, if we attach to the semiconducting surface, it can improve the huge number of charge carrier generation inside the semiconducting material. So that's how the plasmonic method works. I don't want to put so many slides to explain these plasmonic, what are these plasmonic effects, how it has been used for photocatalysis. So just I briefly uh, uh, explained, okay, this is plasmonic effects. In my case, I haven't choose gold or silver because we really want to make it cheapest material, and aluminum is cheapest and earth abundant. That is the reason why I choose aluminum. So in my case, I decided to prepare aluminum nano triangles using colloidal lithography method. So these are the steps involving in colloidal lithography. So we have to take the fused silica substrate, and then we have to spin coat the polystyrene bead. Uh, Once the spin coating is done, or one can also do the same thing with the Langmuir-Broglie technique, and we get the polystyrene nanocrystal. If you look at the right hand side is same image of the polystyrene nanocrystal. This is the real case how it looks like on the substrate. And then we deposit uh, let's say 50 nanometer of aluminum on top of this template, and once we lift off the polystyrene beads, we will get this type of nano triangles that you can obviously see in the SEM image shown here. So this is how I prepared. And you probably ask, how large is your sample? And in my case, I prepared 2.5 centimeters square. And this type of method, we can also prepare few centimeters square, like 10 centimeters square, larger substrate can be prepared. So with this aluminum, you probably ask what you are going to do or how you are going to break the nitrogen molecule. So I'm not used aluminum alone. I combined with titanium dioxide semiconductor. And in this case, as you can see in this schematic of the electrode, so once I fabricated the aluminum nanotriangles, I deposited about 100 nanometer of titanium dioxide semiconductor on top of it. So in my case, who is generating the charge carriers, or from where the electron to reduce the nitrogen molecule is coming from, is from TiO2, obviously, because aluminum can improve the charge carrier generation in TiO2 through plasmonic near field coupling. As you can see, the green curve, the ammonia produced using just titanium dioxide semiconductor is just 0.04 micromolar per hour per milliwatt power per centimeter square, because of the surface area we have to mention. Once we embedded with the aluminum nanotriangles, you see it's more than 2.5 times enhancement. So 0.1 micromolar per hour. You can see in the graph, it's the red line. This is after aluminum nanotriangles embedded. So that's why we propose this schematic in my work, that once we shine a light on aluminum nanotriangles, it can enhance the charge carrier generation from the TiO2 semiconductor, and that electron enter into the lowest unoccupied molecular orbital of the nitrogen molecule, and there it probably form some intermediates called some nitrogen radical or N2 minus before it convert into ammonia. So the exact mechanism still has to be explored, but at the end we were managed to produce some micromolar concentration of ammonia. That's the good news. Okay, you might ask that the efficiency. What is the efficiency of your method? Because if we say, okay, my method can be a suitable alternative for the commercial existing Haber-Bosch process, one would ask the first question, what is the efficiency of your process? So if you look at the current industrial process, the efficiency is 10 to 15%. The Haber-Bosch process I am talking about. So in my case, you can see the efficiency is very low, 0.06%. So this is less than 1%. Is it only you or all researchers so far able to reach this much efficiency? So this is the question. Yes. So a lot of research so far for the last 30-40 years able to reach solar to this ammonia conversion efficiency is still less than 1%. So that is the reason why we were not able to make the technology we developed or the method we developed into practical application. So you would ask, okay, then when it will be available for practical application, when we can stop to pollute our environment with the carbon dioxide, when we can save the energy. The answer is, when we were able to reach the efficiency 5 to 10%, it will be ready for the commercial application. But it is not as easy as we think. It's very difficult. And also the the stability of the photocatalyst we use, it's supposed to be few years at least. But currently, the stability we observed so far has been only few weeks to few months. This is not sufficient. We have to have few years. And I would imagine as a researcher, in definitely in 10 to 20 years, we will able to reach this ambitious efficiency of 5%. And that's the day we are going to celebrate, or we are going to stop the usage of the fossil fuel, methane, all this. Okay, next we move to this second topic, the same solar driven process, but instead of ammonia, here I'm going to show you how the hydrogen can be generated and what are the importance and what are the difficulties we have so far, is how far we are to reach the practical application. So these all we are going to discuss in the second uh, topic. So we all know that every year the world population keep increasing. So whenever the population increase, obviously the demand for energy is high. So that obviously related to environmental issues, because the energy all that we are using, we are getting mainly from fossil fuels. So you can see the fossil fuels we are currently using is 86%. So 34% we are using as oil, and 28% coal, and 24% natural gas, which is methane, and other sources for energy generation is only 14%. And this is again threatening that about nearly 2050, the energy needed, or energy consumption we needed would doubled. So that time we have to have any alternative source for energy in addition to the fossil fuel. So here again, that what I explained in ammonia synthesis as well, the concern about environmental issues and concern about the energy, so alternative energy source. So these are the two major fact we take into the um, mind, and we are keep working on to find suitable alternative fuel. In this case, uh, uh, is hydrogen. So how or where we can see the enormous amount of energy? If you look at the sunlight, the energy we receive per year, which is 1.9 10 to the power 18 terawatt per year, and the energy we use not from solar light but with fossil fuels, we are consuming the energy of 1.3 in 10 to the power 5. So if you compare these two numbers, you can clearly understand that sun provides more than 1,000 times energy that we need. So this is the ultimate way to use sunlight for our future energy demand. And now the question is, okay, sun has enough or more than 1,000 times higher energy than what we actually consumes. But how do we harvest? How do we use it? How do we store the solar energy? Obviously, the solar cell, we all know that how the solar cell works, and solar cell really convert the solar energy into the electricity. This is again with the help of the semiconducting material, p-type, n-type silicon, which is currently the commercial solar cell material. But the drawback of this solar cell is that we cannot really store it for few weeks or few months or few years. We can really harvest the energy, but we have to use it as soon as possible. Or we can maximum store for a few days in a battery. That's it. But we cannot store it for few years like petrol or diesel we store currently. We can store it for maximum months or few years. But this solar cell generated electricity, we cannot store it such a long time. So that's why we really interested to convert this solar energy into chemical energy, and we want to store all this solar energy in the chemical bonds. And you probably have a clue from the nature always, and in this case the photosynthesis system. If you look at the photosynthesis system, it in the presence of the light, it takes carbon dioxide and water and make carbohydrate, and the all the energies are stored in chemical bonds of the carbohydrates. Similarly, we want to store the solar energy in the form of hydrogen. So before see how one can um, produce hydrogen with the solar energy, these are the current utilization of hydrogen. So in our day-to-day routine, we are using hydrogen in different ways. So the main uh, source of hydrogen utilization as a feedstock is ammonia production. As I explained in the first topic, we need to produce hydrogen to combine with hydrogen. That hydrogen we are getting from fossil fuel methane, and that is 55% of hydrogen have been used for only this ammonia synthesis process. And then it has been also used in some refineries to extract the oil, um, the diesel and gasoline extraction from crude oil, and also to produce methanol. And this methanol has been vastly used in polymer industry. Apart from that, some other applications are listed here, like metal alloying, glass production, electronic industry, preventing corrosion in power plant pipelines, and steel manufacturing. These are some other application have been, hydrogen have been used as a feedstock. So these are the um, application where hydrogen indirectly used as a feedstock, but can we can also use hydrogen as a directly in hydrogen fuel cell. So this is zero carbon process, so it doesn't emit anything. As you can see the animation over here, so once the hydrogen is introduced into the anode material, it will generate the electron and holes, and then it reach the cathode. So the current will be stored here, and the oxygen we supplied from the cathode will convert finally into the water vapor, and it produce certain heat. So the output is only air and water vapor. There is no carbon dioxide, there is no other carbon products which heavily pollute the atmosphere. So this is pollution free, zero carbon process. So hydrogen fuel cell. Currently there are some fuel cell cars, some fuel cell vehicles has been used, but if you look at the source for hydrogen, still we are relying on, we are depending on methane as a source for hydrogen. Here are some example. It has been used, the fuel cell, hydrogen fuel cell has been used to supply electricity to the aircraft, and there is some ship propulsion which are in currently in trial basis. Fuel cell powered rail vehicles which are currently run, and some electric buses and passenger cars. I think Toyota going to introduce this year this hydrogen fuel cell car, but these are very expensive, and again the source for not from really the water, it's from the methane. Okay, so now we can see what are the different methods have been developed so far to produce hydrogen from water with the help of solar energy. We can classify into three major categories, like photovoltaic assisted electrolysis, so the left hand side. So from the term itself you can understand the photovoltaic, so the solar cell which generate the electricity can be applied to the electrodes to uh, split the water molecule into hydrogen and oxygen. And this is it has two types based on how we design the electrodes, so like kind of wired system or monolithic system. In the second case, which is a photoelectrochemical, and with this photoelectrochemical, from the term itself you can understand photoelectrochemical, so Here we directly use the sunlight. There is no solar cell. uh, Sunlight directly can make water splitting. So it can also classified into two subsystems, and one is photoelectrode electrode, which means on one side photoanode. So the solar energy directly oxidize the water and produce oxygen, and then the we have to apply some external bias to produce hydrogen from the cathode. So that's why in this case as well little bit applied bias from externally. And this is unassisted system called tandem cell. In this case there is no external bias. It's purely driven by the solar light. So this is highly interesting, and a lot of people believe that compared to all these previous three cases, the system using no external bias can be a potential alternative for potential routes to produce hydrogen for energy source. And this is the number three section called photocatalysis. And in this case, this is the topic I'm currently working on, photocatalysis. In this case, one can directly split the water molecule using the solar energy by just taking the semiconducting powders in water. We have to just take a suspension of the photocatalyst powder in water and then shine a light, and then we can produce hydrogen and oxygen. The same powder we have to make as a film. So we have to prepare some suspension and then paste on substrate. And in this case, we can make like as large as we want. Let's say 1 meter square or 10 meter square, whatever the size we want. So this kind of system recently has been highly focused compared to the suspension system to improve the efficiency. Okay, you probably come to the question that okay, there are different methods you explained how to produce hydrogen using solar energy, but which one I can choose, or which one going to be produce hydrogen very efficiently? So we have to look in few ways, not just the efficiency. We have to look, so the system complexity, it's supposed to be very less complex, then only it will be easily one can produce hydrogen in a large scale. So if that is the case, so the one that I explained in the last, so the photocatalyst film on substrate, this is very easiest way to handle with. And in the case of solar efficiency, of course, so this method all if we were able to reach solar to hydrogen, this STH is nothing but solar to hydrogen conversion efficiency. So we have to have 10% at least to make it solar hydrogen for practical application. So let's see how we can achieve this much percentage, and where we stand, and what is the current or up to date the efficiency we reached so far. Okay, before seeing that, just I would like to show you how the particulate suspension system works. So this is currently I have developed a particle suspension system in a Z scheme based uh, photocatalysis. So that I will explain in the next slide what is the Z scheme. So let's see first what is a particulate suspension system. So in this case we take only single photocatalyst. You can see this is the semiconducting photocatalyst, and in order to perform uh, reduction and oxidation, so H2O to O2 is the oxidation and proton to hydrogen is the reduction reaction. So we have to have both the half reaction simultaneously. Otherwise what will happen is, for example, um, my material has a band gap which can um, which can perform only the reduction reaction but not able to perform the oxidation reaction, what will happen is that the holes we generate in the valence band corrode the photocatalyst material. So the photo corrosion can happen. In the case if we harvest these holes for this oxidation reaction, the photocorrosion can be avoided. So that is why we have to have these two half reaction, oxidation and reduction simultaneously. For that, the energy, as you can see, the energy need to be minimum, theoretical minimum is 1.23 volt, but in reality, any material have to have the energy higher than the 1.23 volt, because in the system it probably needs some over potential to activate the water splitting. And mostly this single photocatalyst for this two half reaction always we require broad bandgap semiconductors, and this broad bandgap means let's say 3 ev or 3.2 ev. Because of this higher bandgap, they can absorb only the UV light from the solar energy, not the visible light. And as I explained, I think in the very beginning of the presentation, only 5% of the solar energy has UV region. So it fails to utilize the maximum solar energy, which is in the visible 45%. And also in this case, the back reaction. So once the hydrogen and oxygen produced, if we take this kind of single photocatalyst system, the water formation back reaction also unavoidable. So these are the restriction by this single photocatalyst. That's why for the last 5 to 10 years, not very old, but it is very recent, researchers are focusing on Z scheme water splitting. So what is the Z scheme? This is nothing but in the natural photosynthesis, it behaves, uh, or that scheme is a Z scheme. Let me explain how it looks like. Yeah, so this is how it looks like, the Z scheme. So before that, yeah, so based on the experimental condition used in the Z scheme, it can be classified into three categories: liquid redox mediator Z scheme, solid and without redox mediator Z scheme. Okay, so here's the schematic for the Z scheme. You can clearly see from here that each photocatalyst, so OEP is nothing but oxygen evolution photocatalyst, HEP is hydrogen evolution photocatalyst. So each material has their unique band gap. See, so this material has its valence band over here, so it has energy less than for less for oxidation reaction. That's why it doesn't prefer oxidation. It prefers mainly the reduction, because this conduction band is higher than this material. So in this case, the advantage is that we can really avoid the recombination of the charge carriers and also the photo corrosion of the material. And as you see, we can choose really the very narrow band semiconductor, so that we can utilize more visible light energy from the solar light. So as there are a lot of semiconducting materials, narrowband semiconducting materials one can use in such a Z scheme system. So in the previous Z scheme that I explained, we use liquid redox mediator. So this, you can see let's say if I take Fe3 plus Fe2 plus redox system, this can consume the uh, holes from the hydrogen evolution photocatalyst and electron from the oxygen evolution photocatalyst. If we change this solution redox mediator, so that is the second system with the solid redox mediator here. So one can use gold, silver, or conductive carbon or reduced carbon oxide as a solid redox mediator in Z scheme. And this is more favorable compared to liquid redox mediator Z scheme, because it can really rules out the ions, the redox mediator ions diffusion, which probably causes some interferences with adsorption of the absorption of water molecule on the surface of the photocatalyst. And this, we believe that this is more facile compared to liquid redox mediator and more appropriate to practical use. However, this is not easy to construct because we have to form double junction. So the junction between hydrogen evolution photocatalyst and the solid metal, let's say gold, and the junction between OEP and this solid redox mediator. That's why we say this is a bit challenging. So this is the system number 3, Z scheme without any mediator. There is no mediator has been used in this system. You can see. So this is the semiconductor A, semiconductor B. Semiconductor A perform reduction reaction because this conduction band is higher than this semiconductor B. So here we produce hydrogen, and in this case the valence band with the semiconductor B, the valence band is deeper than semiconductor A. So the water oxidation can be performed with this. So what happens with these unused holes and unused electrons? They recombine itself at the junction. But in order to form this unique junction between two different photocatalysts, this is very challenging, but it is possible. Probably we have to have suitable binding, let's say the chemical adsorption between these two material or electrophilic adsorption between these two materials, so that the electron or the holes can be exchanged between these two materials. As I said before, this is a bit challenging compared to the previous two systems. But it is possible. Okay, so previously we have seen a lot of methods, and then we see which method can be more practical, and then uh, which method is more feasible between single photocatalyst or dual photocatalyst. And now all these photocatalyst system, how we can evaluate the system, or what's the parameter we take into the account to say, okay, this system is better than this. So here are the 3 parameters: rate of gas evolution, apparent quantum yield, and solar to hydrogen conversion efficiency. So these are the 3 main parameters we use to evaluate the photocatalyst system. And these two, apparent quantum yield and solar hydrogen fuel efficiency, is the highly accurate or reliable form of measuring the efficiency, because this rate of gas evaluation can be it can be varied depending on the different circumstances in the in each laboratory. One probably use the very high power solar energy lamp like xenon lamp or any other lamp, and some people use less energy lamp, some people use monochromatic radiation. So there are a lot of confusion. So one cannot really say that, let's say one group shows 100 micromolar per hour and another group says 500 micromolar per hour, and they cannot claim, this 500 micromolar gas produced group cannot claim that we have the superior activity, because there might be this kind of issues that we discussed before. So these two parameter, apparent quantum yield and solar to hydrogen conversion efficiency, these two are more reliable and accurate evaluating the photocatalyst system. Okay, so where we stand, so same to ammonia, same like 30 to 40 years people are working in water splitting to produce hydrogen as a fuel. But what is the maximum efficiency, or what is the breakthrough we achieved so far? So you can see it from here, since from 1972 the first study, they demonstrate how hydrogen can be produced from water photochemically. Recently in 21st century. This is again, but not less than 1%. In ammonia case, it was still not able to reach the 1%, but for hydrogen, we were able to produce 1 point some percent, because this is my recent work. That's a very breakthrough work. We were able to produce hydrogen 1.7%. But the problem is the lifetime. So the lifetime of the photocatalyst material still in months, not like years, and that's why it is not economical. If you want to propose one practical uh, something into practical application to the routine life, it has to be more economical. It has to compete with the existing technology. But currently, with this 1% of STH, it cannot be achieved. So, what are the conditions we are expecting as a goal, or what is the condition we are really working hard to achieve this position from 2020 to 2050? And this is uh, provided by US Department of Energy and Japan Ministry of Economy. They assume that in the case of, if we able to reach the solar to hydrogen conversion efficiency 5 to 10% with the lifetime of the photocatalyst 5 to 10 years, one can easily get 1 kilogram of hydrogen for 2 to 4 US dollar, and that's the day we can celebrate this zero carbon energy in our everyday routine life. And I hope that definitely it will be reachable, because when this was started in 1970, the efficiency of this STH was very poor, let's say 1 to 0.001%, but now 1,000 times better efficiency we achieved. In the next 20-30 years, definitely we can multiply it to 5 to 10%. So that's, I hope definitely we will reach the benchmark efficiency in the coming years. Okay, so what are the strategies one can use or one can adapt to improve the efficiency to make it 5 to 10%? So these are the major strategies, like a co-catalyst loading. The co-catalyst is nothing but it will add it on the surface of the photocatalyst to extract the charge carriers from the material more efficiently before the recombination. So co-catalyst loading has to be studied still more detailed, and we can optimize the co-catalyst loading like 1% or 2% of the co-catalyst or 3%, which is producing the hydrogen maximum. This has to be optimized, and it vary from material to material, and there are so many co-catalyst materials are available currently, so we have to screen this co-catalyst material. And the second thing is the surface engineering. So surface engineering is nothing but we have to engineer the surface to make the molecular adsorption very strong. If you want to produce more hydrogen from water, the surface should be more hydrophilic, or it should form chemical bond or chemical adsorption of water molecule on the surface of the material. So this is why we say surface engineering is very important. It can be studied by density functional theory as well. So they can first take some materials and then study their surfaces, how the atoms are looks like, and which kind of surface supports the chemisorption of hydrogen um, production. So the third strategy is the morphology control. So this is another important parameter, that if we were able to make, let's say, some sharp edge material like nano sheets or some triangles, in these cases the edges are very sharp, and these edges can be act as effective active sites, and more molecules can bind more specifically onto that surfaces. So the morphology, in addition to the size of the material, as well, very important strategies has to be optimized to improve the hydrogen production efficiency. And the crystallinity of the material. So crystallinity is nothing but whatever the semiconducting material we synthesize chemically in lab, The unsynthesized material is mostly amorphous. So amorphous materials are um, not good in the sense that the charge carriers generated always recombine inside the material. We cannot make the diffusion of the charge carrier to the surface. It's very difficult in the amorphous form. So it has to be converted into crystalline form. For that, one can use the annealing condition or heating the material to a certain temperature to make it crystal. So this crystallization also reduce the defect sites present inside the material. So we have to reduce the defect density. So this is the another strategy I said. So by improving the crystallinity, one can really control the defect density in the material. So these are interrelated. These two strategies are interrelated. And this is the another important strategy. One has to focus on this, that the field I was working in EPFL. So the plasmonic nanomaterials. So plasmonic nanomaterials has very unique properties to harvest the solar energy, and these materials can be combined with the photocatalyst material, because these photocatalyst materials may be poor solar absorbing material, but by combining the plasmonic material into the photocatalytic material, we can efficiently harvest the solar light, and that solar light can be directed to the photocatalyst to produce more charge carriers inside. So this is like a antenna reactor concept. So plasmonic materials can act as an antenna to harvest the solar energy, and the reactor is the photocatalytic material, like any semiconducting material. So these are some strategies I wanted to present. For all these strategies to explain one slide, but probably it would consume more time. That's why I just briefly explained these strategies are has to be improved to enhance the efficiency. Okay, I think we are very close to end of the session. So what are the future outlooks? In addition to all these strategies, what are the other things one can focus on to reach that practical application stage? So we have to promote hydrogen production faster than oxygenation. This is nothing but to improve the lifetime of the photocatalyst, to avoid the photocorrosion of the photocatalyst. As I explained in the roadmap of the benchmark efficiency, the lifetime we reach so far is only few weeks to few months. In order to reach few years, this has to be applied. So the reduction reactions should be faster than the oxidation reaction, so that we can avoid the oxidative decomposition of the photocatalyst, which is nothing but photocorrosion. And we have to reduce the over potential. I think so the over potential is nothing but whenever we take some complicated reactor system, we have to apply more energy to break the water molecule, water splitting. So if we choose the right or more suitable surface of photocatalyst and a co-catalyst, we can reduce the over potential, and so we will get higher efficiency. In the case of Z scheme, if so far Fe3 plus Fe2 plus redox couple, or I minus IO3 minus redox couple, these two are very common redox couple used in Z scheme. So they have some stability issues. They are pH dependent. If, for example, Fe3 plus Fe2 plus work very well in acidic condition, but not very well in alkaline condition. Same like I minus IO3 minus, or very good in alkaline condition but not in acidic condition. So this is the issues. So if we will be able to come up with some new redox couples, it can work on both alkaline as well as acidic condition. That would be good, and we can really use it for long-term applications. Yes, this is another important issue, that we have to separate the products. Once it's produced on the surface of the photocatalyst, we have to have some engineering of reactor technology to separate these two materials immediately. Otherwise, this can explode. As you know, the hydrogen is a fuel, and oxygen it can make explode. So we have to have sufficient extraction technology uh, to not mix these two gases. And construction of tandem system. So the tandem system I explained, it's a photoelectrochemical, not a photocatalyst, a photoelectrochemical. We take both electrodes, anode and cathode, and they work only with the sunlight. There is no external bias we needed. So we have to construct more efficient tandem system as well to achieve our breakthrough efficiency. Similarly, we always need interdisciplinary research between experimental chemist and theoretical chemist to address the challenges in whatever the field we use or whatever the field we study. So there are currently less study on Z scheme system, and theoretical study on Z scheme system is only very few have studied so far. So we have to optimize few parameters by combining experiment and theory. Yeah, as I explained before with the plasmonic nanometer, this antenna reactor concept also has to be optimized, and one can work in future to make a very efficient antenna reactor system to produce hydrogen more efficiently. Last but not least, we have to have whatever the system we develop, the cost should be very less or very cheap, then only we can talk about the practical application or available to the market. And that's it. So thank you for your patience and listening, and I would welcome your questions. You can ask me, or you can also email me to this contact, to my official email as well as my personal email. And once again, I thank for the organizer who give me a chance to share my research work with you guys. Thank you so much.